So we'll continue with quicksort analysis today. So recall last time we looked at the average case analysis for quick select, which is a randomized algorithm to find the kth smallest element, and quicksort. So quick select, we did the average over all possible choices of the pivot, wrote down some recurrence, and I asked you to verify its linear time. For quicksort, we saw in a very similar way some sort of a recurrence, but I also gave you another slick argument to show that if so in quicksort we said if xi is the ith smallest element and xj, okay, then probability that xi and xj are compared in this algorithm is 2 by j minus I plus 1, because this is exactly the probability that in between xi to xi plus 1 to xj, either xi or xj is picked as a pivot before everybody else is picked as a pivot, and that had this probability, and that simplified the whole thing to get some expected number of comparisons overall became summation I summation j greater than I 2 by j minus I plus 1. This is some n times or 2n times hn, where hn is the harmonic sum, and that gave us this bound of expected n log n bound for quicksort. Okay. Now, what we want to do is to see what is the probability that it's not very much more than this. Okay, we want to analyze. Remember the probability space is there is all possible pivot choices, not at the beginning but at every recursive step and so on. Among all those choices, we want to now. So this expectation exactly tells you that just do these random choices for every pivot, average over all possible choices at every recursive step, and overall the average number of comparisons is this. That's what this expectation tells you. But I want to understand, often this is very useful in randomized algorithms. It's not just we want to compute the expectation. We also want to know what is the probability that the algorithm will take more than, let's say, 10 n log n time, and I want to upper bound it, and I want to argue that somehow that happens with very small probability, and we want to bound that. Okay. So towards that, what are called tail inequalities. I mean, if you think about it, what we are trying to do is that you have some distribution, right? So let's say this is the number of comparisons, and these are different sample space, right? Different choices for pivot. For some choice, maybe the algorithm takes this much time. For some choice, it takes this much time, maybe this. And what we are saying is this average is 2n log n. Now I want to say, okay, if the average is 2n log n, I want to go a little bit more and say, okay, how often does it take really much more than this? Okay. Now it could happen depending on your distribution that let's say the average mark is 100, but it's possible that half the people are way above 100 and half the people are way below 100. Okay, then the average with some distributions where this happens. So it is possible that half the guys are way above the average, and I want to argue that in this case for quicksort it is not like that. The probability that's way above the average is very small. Now, how do we argue this in general? So that takes us to this notion of tail inequalities, okay, in the probability space. Okay. So I'm going to assume some standard things in case of probabilities, I think you would have done some course, but I'll tell you what assumptions I'm making. So I assume you know what it means by events being independent, and I assume you know what it means by expectation of a random variable. What is a random variable? What is a space? All that. Okay. So a sample space basically is, this is a sample space, and this is basically the set of outcomes. Right. So if I am tossing a coin once, then there are two outcomes, head or a tail. And if it's a fair coin, so each outcome has a certain probability associated with it, right? So probability that this random variable gives this outcome, so that is also given to you in advance. Okay, so if and there is a notion of expectation, which is basically the average, right? So expectation, so if x is a random variable, then expectation of x is basically, so think of a random variable as, a function, right? It just gets any one of those outcomes. So you can think of an average of your marks. So random variable is a mark, and there are this whole bunch of marks, and the expectation is essentially the average, which is, probability that x is equal to whatever w times the value w, where w is in your space, right? It's like how many people got 10 marks. That's essentially what is telling you the probability. Multiply by 10 and run this over all possible values of marks. That gives you this average. Okay. So we knew all this. That's what we used to compute that the expected number of comparisons in Quicksort is, at most exactly 2 log n, right? 2n log n, where log there is to the base e, okay, natural log n. Okay. So here is the first inequality. Again, you might have seen this. Which simply says that probability that x is greater than k for some value k is at most expected value of x by k. Okay. So it's like if the average marks is 40, let's say, so yet expected value of x is 40 and my k is 80, how many people would have gotten more than 80? At most half of them. Right? So Ex by k, because 40 by 80, that's it. At most half the number of people would have gotten more than 80, because it's not possible that it's more than half, because then if you multiply, it goes above the average. Okay, so it's very, very simple to prove this. So what this is saying is, so your random variable x takes various values whose average is E of x, and what they're saying is that probability x is greater than k means that, the proportion of the people who got more than k is at most the average by k. Okay, so we'll have a running example to check this, but how do I prove this? Proof is not very hard. So what is the expectation of x? This is summation over, all values of x, as I said. Okay, so this is greater than, suppose I restrict it to w is greater than or equal to k. Right, and just written the same thing. Now I'm not running it over all possible values of your sample space, but only for those which are greater than or equal to. So I put this as greater than or equal to. Okay, now since w is greater than or equal to k, I'm going to take k out and say that this is basically But what is this? This is basically the probability that your value is greater than or equal to k. So now bring the k to the other side. What you have is what you want. Okay. So let's have some running example here. Okay, I don't want to do quicksort. Let's look at some very simple example. Let's say I have given an array of green and red balls. Yeah, so let's say there are some n green balls and n red balls. Okay, totally there I have 2n. I have an array of 2n balls. Half of them are green, half of them are red. And I do the following experiment. What is x? So repeat k times the following. Get ai for some random I. So I have these green balls, red balls in my array. Okay, somewhere, some of them are green, some of them are red. So what I do is pick a random number and go to that location and get that color of that ball. And my xi, so this is what I'm going to, I repeat this. So xi is 1 if ai is green, let's say. So if I find a green ball, it's a success for me. Otherwise, it's failure. Okay. So this I and this I are not. Okay. J equal to 1 to k. I pick a random integer, go to that location. If I find that green, then my xj is set to 1. Otherwise, it's 0. And then go to the next time. I repeat this basically k times. And my x, the random variable x, is going to be x1 plus x2 plus xk. This is my random variable. This is a random variable because it's sum of k different random variables. Okay, why is a random variable? Because I am consulting a random number and going to a random location. So I don't know what I will get. So my outcome, there are two outcomes, green or red. And what is the probability that xj is 1? Half. Because there are exactly half red balls, half green balls. They are distributed somehow. I'm going randomly, I'm picking 1. So I'm not biasing towards any location. They are arbitrarily distributed, but I just go pick a random location. So it's probability half. So
K is not random.
k is some fixed number.
So x is bounded by k.
Yeah, x is bounded by k. Yes. Sure. So I want to analyze the value of x. This is my x here. This is a random variable, which is the sum of this. I mean, basically, what is x? X is the number of green balls I got in this k experiments. The number of green balls is x. Okay. So x, as you said, is at most k. What is the expected value of x, right? K by 2. So again, why? Because first of all, this is one of the important properties of the expectation, that this is called the linearity of expectation. If you have sum of some k random variables, it may or may not be. In this case, they are independent because my experiments are completely independent. But this linearity of expectation holds even if these events are not independent. But anyway, so expected value of x is sum of this. What is the expected value of any particular random variable? Let's apply this formula. Right, for each one, there are exactly two outcomes. Right, so it's 1 with probability half plus 0 with probability half. So it's half. Right, so 1 into half plus 0 into half. So that's half. This is half all of this. So this is k by 2. Okay, so this is intuitive, right? Because if you have a probability of half getting ahead, and if I toss some k coins, I'll get k expected number of coin heads is k by 2. That's what this is saying. But what I would be interested in knowing is what is the probability that I get 3k by 4 heads, let's say, right? So that's the kind of questions I'm interested in. How, what is the probability that my variable, random variable, takes a value somewhat larger than the expectation? You can also ask the question less than the expectation, but Markov inequality doesn't say anything about less. It only talks about greater. So, from Markov, for this experiment, this is the running experiment for all the inequalities. Probability that x is greater than 3k by 4 is at most expected value of x by 3k by 4. And what is expected value of x? It's k by 2 by 3k by 4. So this is at most 2 by 3. I mean, this is exactly, k goes away and the 4 comes here. Yes, so with probability at most 2/3, it's at most 3k by 4. Okay. Again, the simple argument is that if it is more, then if you multiply this by this, you get more than k by 2, more than the average. Right. So basically, if the average is something, you cannot have too many people with much more than the average. Okay, so that's what's the argument. This is for any random variable. You're not talking about x. It so happened that x is obtained this way, but this inequality is true for any random variable. Okay. Now it turns out it can actually say something even stronger. This is very, very weak. It just says at most 2/3, but I will tell you. If k is large, if I do large number of experiments, then we will argue that the probability is even lower. No, but Markov doesn't give you that. We need other inequalities to show you. Okay? So this is one useful inequality, which tail inequality, because we are talking about sort of the right tail. Okay, if you think of your distribution, right, as I said, x takes value something, 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 something. Now this tells you what is, this is your k, then it tells you what is the probability that my variable takes value greater than k. Okay, so it's sort of this tail. Okay, so this is for any random variable. Another popular inequality is called Chebyshev, which requires you to have know the variance of the distribution. Okay, so what is the variance of a distribution? Is the expected value of x minus ex whole square, basically, right? So compute x takes various values. For each one of them, see how far it is from the average, because expected value of x is how far it is from the average, and essentially take the average of these distances. But this could be positive, sometimes negative, so it's convenient to just square them and compute the average of it. Okay. Then Chebyshev's inequality tells you probability that x is greater than or equal to,
X minus probability expectation of
x minus ex, right, is greater than or equal to t times sigma is less than or equal to 1 by t square, something like this.
or maybe sigma comes to this side.
Yes. Sigma by t square. Okay, how do we prove this? Okay, before we do the proof, let's see what Chebyshev's inequality gives you for this probability for that experiment. Okay. This, by the way, this is also same as e of x square minus e of x whole square, right? Take the expectation of the value x square and subtract from the average square, and this is the same as this. You can verify it. So let's compute the variance here. So expected value of x is k by 2, we have seen. Oh, also yes, but before I do the proof, we need this little lemma. Expected or variance of x1 plus x2 equal to variance of x1 plus variance of x2 if x1 and x2 are independent. These are independent events. Then you need the independence here. You can verify this because you just use the definition and use the property that if two events are independent, then the probability, the expected value of the product x1, x2 is equal to e of x1 times e of x2. So you need to use that and use the definition to prove this. So now in our case, these experiments are repeated independently because I pick a location, look at the color. I don't do anything, repeat the same experiment, independently pick another random location and look at the color and so on. So these are independent. So let's compute the variance of each of the xi's. What is variance of xi? By definition, this is the expectation of xi square minus exi whole square. What is the expectation of xi square? Xi takes value 0 or 1. So xi square is the same as xi. So that expectation is also same, right? 0 with some probability half and 1 with probability half. So it's half. Expectation of xi is, so it's 1/4. So this is 1/4. So variance of x would be, you sum them up. In fact, this is true not just for two events, you can generalize it for multiple events. So for k events, so you just add the variance of each one of them. So that would be like k by 4, right? 1 by 4, 1 by 4 at each place. So So probability x is greater than 3k by 4 is what I'm interested in, is equal to probability that x minus k by 2, because that's the expectation, is greater than or equal to k by 4, right? Which is less than or equal to sigma, which is k by 4 by t is k by 4, so k by 4 square. So this is equal to 16 by k square. No, sorry, 4 by k. Right? So all I am doing is now we use this extra information, which is also called the second moment, which turns out to be k by 4 for this experiment. So now if I want to know, this is the same question as this, I can write this as x minus k by 2 is greater than or equal to k by 4, because 3k by 4 is k by 2 plus k by 4. K by 2 is the mu. So it's x minus the expectation is greater than or equal to k by 4, which by Chebyshev inequality is at most sigma by t square. This is sigma k by 4 by k by 4 whole square. So this is 4 by k. And notice that this was, it's the same experiment, right? We didn't do anything. Same experiment, same random variable. By applying a different inequality, we get a much better bound, because this says is at most 2/3. This says is at most 4 by k. So if k is really large, if you do this experiment 400 times, then this tells you it's at most 1 by 100 is the probability by which it's going to be taking more than 3k by 4. Whereas this is always saying 2/3. Okay. Is that clear? So let's, the proof of Chebyshev is not very hard. So you apply Markov's. So probability that x minus ex whole square is greater than or equal to t square. Compute this, okay? So let y be x minus ex whole square. Then if I apply Markov's inequality for y, then probability y is greater than or equal to k is at most ex by k. So this is at most ey by t square. And what is ey? Ey is essentially sigma, is what you can check, right? But what is ey? Oh, I have already written down here. So what you get is sigma by t square. So no, same came. Okay. So ultimately think of, I'm trying to estimate this, right? So I have some experiment, because that's sort of the goal in Quicksort. I mean, it turns out this kind of simple thing doesn't work there for Quicksort. You need to do something else. But I have this experiment, I have this random variable, I have computed the expectation. I want to know what is the probability that the variable takes value much more than some fraction, something more than the expectation, right? So that is sort of this kind of a question. Markov works for any random variable, and it's pretty simple. It just gives you some bound. But Chebyshev gives you, if you know the variance, it gives you a better bound. And if you know higher moments, which is expected value of x minus ex whole cubed and things like that, you can prove some slightly better things. Now, there is another inequality which is very powerful, and that is applicable for some special cases like here, and that gives you even better bound. Okay, so let's capture what we have shown so far for this experiment. Probability x is greater than or equal to 3k by 4 is at most 2/3 by Markov, and it's at most 4 by k using Chebyshev. And it required computing this variance, right? So this is inequality due to Chernoff, which is more powerful, but it doesn't work for any random variable. If it works for this kind of random variable, suppose x is equal to some x1 plus x2 plus some xn, where the xi's are mutually independent, like in our case, right? Because, and we'll see some dependent events to understand this and this notion of independent, and also they're called Bernoulli, which means takes value 0 or 1. So essentially, let's say 1 with probability pi and 0 with probability 1 minus pi. Then for these kind of random variables, probability that x is greater than or equal to 1 plus delta times expectation is less than or equal to e power delta by 1 plus delta power Okay, let me just check this exactly. For any positive parameter delta. And what is expectation? What is the expectation for this random variable x? Because each xi will take 1 with probability pi and 0 with probability 1 minus pi, summation pi, right? Mu r. Mu is the average or expectation. And there is also analogous bound for x is less than or equal to 1 minus delta if x as well. Same thing. So notice that Markov's inequality tells you what is the probability that x is above a certain limit. It doesn't tell you what is the probability that x is below a certain limit. I mean, the way it is proved, it doesn't give you. Whereas Chebyshev, because of the modulus, it does give you both sides. And similarly here also, we can bound the probability that it's 1 plus delta times Ex or 1 minus delta times Ex. That if it's right. So if your Ex is here, then we are trying to compute, what is the probability that it is more than that or less than 1 minus delta times g of x. And it doesn't need variance computation, makes life easier. So it just says, delta is any parameter you can apply, but you can apply only in this case where x is the sum of some n random experiments and each one takes value 0 or 1. And it happens quite a lot in many of the randomized algorithms. So it actually works for these things, many cases. So let's again try it for our question before we prove this. So if I want 3k by 4, then what is delta? Expectation is k by 2, right? 1 plus delta is 3 by 2. So delta is half, right? So if I want to compute this quantity for our experiment, right? Because expectation is k by 2, so it's 3 by 2 into k by 2. So delta is half. So if I plug it in here, what happens? Let's see. So if I so delta is half, right? So e power half and 1 plus delta is 3 by 2. So 3 by 2 power 3 by 2. The whole thing power k by 2, because that's the expectation. Okay, so how does it look like? So it's e by 3 by 2 whole cubed. So I'm taking the k by 4. Okay, so or let's say more 8e by 27. Okay? 3 by 2 cubed is 27 by 8. So I've taken this 2 in the denominator outside, and 3 by 2 cubed I have replaced it by 27 by 8. So 8e by 27 power k by 4. So how does 8e by 27 look like? E is between 2 and 3. So 27 is a much larger number than 8e. So it is something like some small number power k by 4, right? Right. So this is like some c power k by 4. So c is some number. Okay. So here also, so now this is saying it's exponentially small probability. As k increases, so this was just giving you 2/3, nothing else. This was giving you 4 by k. As k increases, it increases, but in a 1 by k way. That's it. Whereas this is saying 1 by c power k by 4. So as k increases, this quantity is going to increase, and so the probability is going to substantially decrease. Okay, and this kind of thing will be very, very useful for our when we want to do some tailbound estimates in our randomized algorithms. Okay, how do I prove this So let's try and prove this. This is more or less the same. So we just need to apply Markov inequality for some appropriate function. Okay, so this is what it is. Probability, we're just going to take the exponent of this. For some lambda positive parameter. We'll for any lambda actually, we will fix lambda later. Okay, because if x is greater than or equal to this, then I just go lift x to some e power lambda x, then that would be greater than or equal to e power 1 plus lambda delta times e of x is this. Okay, we'll choose the best lambda possible later. So now I'm going to compute this, and at some point I will apply Markov's inequality. So I'm going to erase this because now you understood the experiment and you see how these three inequalities give you progressively better and better probability bounds for this question, right? Okay, so we're going to apply Markov's for e power lambda x. Okay, so then this is going to be less than or equal to thing expected value of e power lambda x by e power 1 plus lambda into summation pi. I've just applied this. Oh, there is a lambda somewhere. So here lambda on both sides. Yes, so there is a lambda here, right? E power lambda x is this. So there is a lambda here. Yes. Yeah, let's compute expected value of e power lambda x. Expected value of e power lambda summation xi, right? Which is same as product over I e power lambda xi, right? Because these two are the same. Right, because lambda summation xi is in the exponent, so e power lambda xi x1 into e power lambda x2 into blah 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 is exactly this. Okay. Since these xi's are independent, I can take the expectation inside. So this is equal to product I expected value of e power lambda xi.